Okay,
I think we're going. All right.
Oh, okay.
So Dmitry obtained 2 master's degrees at the ETH Zurich and at the University of Geneva, having been supervised by Lydia Del Rio and Renato Henner. He spent 1 year as a visiting researcher at the IBM Zurich and now is a PhD researcher at the University of Amsterdam and CWI. His research interests lie in the areas of quantum computation, quantum algorithms, and mathematical physics. Let us all welcome our speaker.
Thank you very much, Leandro, and yeah, thank you very much for inviting me to give this talk. Yeah, so my name is Dmitry, and I'm a PhD student, as you said, at University of Amsterdam, and more specifically, the research group called QSoft. And I'm going to present my joint work with following amazing people. Werner Allerstoffer, Matthias Christandel, Jon Nikita, Maris Ozels, Denis Rochette, and Philippe Verdun-Lunel. Yeah, so as you can see, we are spread all over the Europe, and the subject of my talk will be the monogamy of highly symmetric states. And my plan for the talk will be roughly as follows. So first, I will try to motivate our problem, which we're gonna solve, and I will introduce the central concept of this work, which is called G extendability. Then I will have to explain some mathematical background needed to solve the problem. And here in the second part of my talk, I will describe mathematical results about Schur-Weil, Brauer dualities, Eutis-Murphy elements, and I also talk a bit about representation theory of Brauer algebra. And finally, I will be able to explain our main result and sketch the proof of main result. So our main result is concerned about the specific type of G extendability, which is Kn extendability, and Kn stands here for a complete graph. And I will discuss this concept applied to 3 classes of highly symmetric states, so-called Werner states, Brauer states, and isotropic states. So let me start. So monogamy of entanglement is a fundamental feature of quantum theory, and roughly speaking, it says that entanglement cannot be freely shared. So in my talk, by the word of monogamy, I will basically mean this this kind of very intuitive idea, and this concept of monogamy has several incarnations in quantum information, and I just wanted to mention a couple of scenarios where the ideas of monogamy of entanglement are crucial. So one is one place where the monogamy of entanglement appears to be very crucial is in the security proofs of quantum key distribution. So to that end, the work of Renato Renner from his PhD thesis is a very good source for reading. Another one is a rather recent example of semi-definite programming relaxation for bilinear optimization by Berta, Borderi, Favzi, and Scholz. And the final example where monogamy appears and is very important is in the studies of ground energy approximations of local Hamiltonians, and more specifically the work of Brandau and Harrow from 2013 was developed to understand how you can approximate ground energies by product states. And all those applications are actually they're all connected, and they use in one form or the other so-called quantum definity theorems. And the quantum definity theorems is, they're like one possible incarnation of the idea of monogamy, if you wish. More generally, if you want to speak about monogamy of entanglement, the most general way to understand monogamy is basically to solve the so-called quantum marginal problem. And this is a notoriously difficult problem, and it was solved by Klashko in 2004 for one-body marginal problems. And we actually know that already two-body marginal problems is QMA hard. And to the end, also the PhD thesis of Matthias Christandel from 2006 might be a good source for reading here. And so kind of understanding the correlations, this is right, and consecutively understanding how entanglement can be shared is equivalent to study quantum marginal problem. But yeah, it's very difficult. So let's try to consider an easier version, or kind of more restricted version of that problem. And so this is what we are going to be focusing today. So we're going to study a restricted version of quantum marginal problem, which we call G extendability. And this notion of extendability, which I will explain in a moment, was already introduced a long time ago. And one work which is very relevant to our work is a work by Wolferstratt and Sirac from 2003 in that context. So let me now introduce this main idea of G extendability. So let's say we have a sigma, which is a bipartite symmetric state. So what do I mean by this is that so the Alice side and the Bob side, so if you permute the Alice and the Bob side, the state is the same. And I say that this state is G extendable if I can find the global state which lives on the graph G, where the vertices of this graph, so these yellow dots, are now quantum systems, right? So d-dimensional quantum systems. And each edge in this graph will correspond to the marginal state rho sub E, right? Each edge of this graph. And I require that each such marginal state is equal to sigma, right? So it's basically, by having a graph, you specify the positions of two-body marginal state which you're interested in, and you want to say that those two-body marginal states are those sigma states, right? And now what you might imagine that you actually have a family of bipartite states, sigma of P. Let's say it's one parameter family where P is a parameter, and the intuition you should have in mind that this P is some kind of parameter which quantifies the entanglement. And let's say the higher the P, the more entanglement you have, right? So we will see more concretely what do I mean by this in when we come to precise formulation of our problem. But yeah, at the moment, just think about this P as being some kind of quantifier of entanglement. And then we can try to solve the following problem. Basically, what we would like to understand, the following numbers, so which are called P sub sigma of G and D, right? So this number is a function of my graph and local dimension. And so I basically want to maximize this P in every edge of my graph, right? So like every edge on this graph corresponds to some two-body marginal, which will be equal to sigma P, and I want to maximize this P, right? So I want to maximize entanglement. Okay, so now I have introduced this concept of G extendability, and now I just want to put this into the context of the very well-known and classic theorems. So one theorem in quantum information, which is called quantum definity theorem, which I already mentioned. So one way to rephrase it using the language which I just introduced for bipartite states is the following. So one can say that if you have a bipartite state, and if it's basically it's kn extendable for every n, so meaning that you can extend it to any complete graph of arbitrary size, that holds if and only if you can write your sigma as a convex combination of this tensor product local density matrices, right? So this condition is stronger than the usual condition for separability. We can call it symmetric separability if you wish. And the other theorem, which again sometimes goes by the name of monogamy theorem, is very similar, but except for the complete graph, you talk about the star graph, right? So, or in other words, it's a complete bipartite graph, right? So you have a kind of one vertex in the middle and surrounding vertices which are connected to this middle vertex. So it's like a star graph. And this sigma is extendable to the star graphs for every n, if and only if the state is separable. Right? So this is a very well-known theorem, like an equivalent statement of separability of a bipartite state. Yes, so we see that using this concept of G extendability, these two theorems can be formulated in a very unified fashion. And ideally, we would like to explore those for arbitrary graphs, but of course it might be very difficult. So let's see what we can do at the moment. Right. So yes, there was a question. Sorry. Okay. I guess there's no question. Okay. So let's so let's go back to our problem, right? So we want to solve the following optimization problem, right? So we want to maximize this measure or like quantifier of entanglement P. Again, it will become clear in a moment what this P exactly means. And yeah, as I said, plugging in arbitrary sigma and arbitrary graph, this seems very infeasible, right? So it's too difficult in general to solve such a problem. So what we are going to do, we will focus our attention to bipartite state sigma, which are highly symmetric states, and so these are we can call them toy example states, but these states are very they appear in quantum information in a lot of context. So these states are so-called Werner states. So the Werner state is essentially is the same as just saying that your state sigma commutes with tensor product of unitary or for every unitary, right? So here the tensor product of the same unitary. The second option will be the so-called Brauer state. So it's exactly the same, except for the unitaries, you put the orthogonal complex orthogonal matrices here. And the third one is so-called isotropic state. So this is equivalent to say that your bipartite state commutes with U tensor U bar. So considering those symmetries will render our problem much more feasible and amenable to, hopefully, to analytic solution, right? And but of course, considering arbitrary graphs is also might be too difficult in general. So in this work, we were kind of doing the first steps to solve this problem for the case when the graph is edge transitive. And in particular, we wanted to consider, in this talk, we will consider two cases. One case when this graph is just a complete graph, and the second case when the graph is complete bipartite graph, right? So you have one set of vertices n, which are not connected, and another set of vertices, like m vertices, which are also not connected, but they are fully connected between between those two sets of vertices. Okay, so this is the setting of our problem. I wanted to. So I guess if you have any questions at this point, you may ask me.
Sorry, quick question. What's the P here? Is the P the probability, or what's the P? Sorry.
Right. Yes. So P at the moment, this is just some quantifier of entanglement. But in later you will see that once I will define precisely how I will write this Werner state or Brauer state or isotropic state, this P will be like, if you wish, it will be like a coefficient in front of the projector, which corresponds to a projector to entangled state, like maximally entangled state or like antisymmetric state or something like this. So intuitively, you can think about it as being, it's like which portion of the state is very entangled somehow. So it doesn't. So in this particular work, this is not really a measure of entanglement, right? In the usual sense of the entanglement measures. But this is a number which can say something about entanglement, right? It can say something about how entangled your state is. So for example, like
So it will give you a value. It's not an operator, right? So you say projectors, but it gives you some measurement, like entanglement, as you say. Okay, correct?
So maybe I will show you in a couple of slides very precise form of this optimization, and hopefully it will become clear what do I mean by this.
Sure. Thank you.
Yeah. Mm-hmm. Okay. So so this will be our optimization problem, which we will try to solve analytically. But before I show you how we solve it, I need to introduce some mathematical concepts. And the first concept is of sure-while duality. So not surprisingly, because we are considering states with symmetries, so we need to understand some representation theory. And so sure-while duality is a classic result in representation theory, which has a lot of different applications in quantum information specifically. And so I will introduce it in the following way. So let's say you have a map phi, which maps a general linear group of D by D matrices, complex matrices, to the space of matrices which act on n qubits, right? So here, so this is a Hilbert space of n qubits, and the action of this general linear group by this map phi is diagonal, meaning that you take any element of general linear group, right, and you'll just multiply every simple tensor here in the tensor product. And then just to be very pedantic, let's introduce the algebra of matrices, which will be spanned by all such matrices, right? So phi of G. And we will call this algebra curly U sub n D. So why actually I call this curly U is because you can actually, instead of general linear group, you can put a unitary group and you'll get the same algebra actually. So now I I need a second algebra, and the second algebra will come from symmetric group now. So and now I'll introduce this psi map, which again a representation of a symmetric group on the same space. And this symmetric group acts by permuting registers, right? Just so here you can see that the indices of this axis are permuted according to permutation pi. And is the way I think about the permutation is like diagrammatically or like more abstractly is that the permutation for me is a diagram like that. So and this diagram encodes how I permute right my systems. And again, I can just formally introduce this algebra of matrices spanned by all images, right, of my permutation, this algebra S. And now the statement of Schur-Weil duality is almost intuitive, but yet not so obvious to prove statement is that this algebra curly U and this algebra S, the mutual commutants of each other. So what this notation means that so this Z of S comma the space of matrices here, it means that so this object is a set of all matrices which come from the space of all matrices of on our Hilbert space, which commute with algebra S, right, and vice versa. So S will be the centralizer. Yes, there's a name for this. Is a centralizer. Is a centralizer of algebra U in this space. Okay. Now there exists a similar notion for orthogonal group of for complex orthogonal group, and yeah, like I will call it Brauer duality. So it was discovered by Richard Brauer. Again, I have my map phi, but now I restrict it to like the domain only to be orthogonal, complex orthogonal group. And now I have my curly O algebra, which is a span of all such orthogonal matrices which act diagonally. And you can see, because the set of orthogonal matrices is smaller than the set of general linears, it will be a subalgebra of curly U. And similarly now, I would need to have a dual, right? A dual algebra, and the dual algebra will came from so-called Brauer algebra. So this Brauer algebra, which is denoted by Br and D, is an algebra which you can think of being spanned by diagrams of that sort. So now, instead of connecting vertices vertically, like we had in permutations, now you can connect these vertices horizontally. And intuitively, this horizontal connection, so we should think about it as being like a projector, if you wish, to maximally entangled state. And then we can consider again the formal algebra, which is spanned by all such matrices, right, which came from this Brauer algebra. And now the statement of the Brauer duality is exactly the same in the original Schur-Weil duality, except now the place of the curly U algebra is played by O algebra, right? And in the place of S algebra, you have this B algebra, which comes from the Brauer algebra. Right? It's in the mutual centralizers. So this is a statement. Okay, so now we understand how. So we understand the Schur-Weil Brauer dualities. Now we go to next ingredient, which we will need to explain our results, so-called Euclid's-Murphy elements. So these are very special elements from which live in the group algebra of symmetric group or in this Brauer algebra. So for the group algebra of the symmetric group, JK Euclid's-Murphy element So yeah, this subscript S denotes that it belongs to this symmetric group algebra. So it's just a sum of transpositions, right? And diagrammatically, I think about my transposition as just permuting the registers I and K, right? And doing nothing on all other registers. Similarly, for Brauer algebra, there exists a very similar element, but now you have this transposition. What you need to do, you need to also subtract this element, which I call a contraction, right? So it's like a transposition, but yeah, you don't permute. You essentially project onto the maximally entangled state between I and K here, and you do nothing on other, like you just apply identity on all other registers. And in the following, it will be also important, and actually we will not really need those Euclid-Murphy elements, which are defined for every K here, right, from 1 to n. But we will actually would need the sum of those elements, right? And more precisely, I would need to think about those sums as being a matrices, you know, in my big Hilbert space of n qubits, right? So that's why I put this psi here. And yeah, I just sum all those Euclid-Murphy elements. And these two matrices, J, S, and JB, will play a crucial role later. Okay, so now I have introduced this Schur-Weil duality and Brauer duality a bit like algebraically, but there is an equivalent way to think about it, and namely, Schur-Weil duality is essentially equivalent to the statement that your Hilbert space will decompose into direct sum of tensor products of irreducible representations of this algebras S and U. And the direct sum here will be labeled by mu, and mu will be essentially a label for the irreducible representation of the algebra S and U. And more precisely, so when I put this hat here, so this means the set of labels of reducible representations, and the set of reducible representations for this algebra S is actually a set of partitions, or so-called Young diagrams, subject to a condition that the size of the first column of the Young diagram is at most d, which is a local dimension. So let's just look at the example, what that means. So yeah, when I write mu, a partition of 4, yeah, so that's how I write this partition of 4, or pictorially I can represent some diagram, some Young diagram like that. So it's a collection of boxes arranged in the non-increasing fashion, kind of from top to bottom. And when I write mu prime, what I do, I do so-called a transposition of a diagram, right? So I kind of I reflect it along the diagonal, and yeah, when I write a subscript, it means that I extract the size of the first row. So in that case, the size of the first row of this transposed mu diagram is 2. And or equivalently, in the original Young diagram, this was the size of the first column. That's how you should read this. And yeah, so it turns out it's a classic resultant representation theory that these Young diagrams, they label the reducible representations of symmetric and unitary and general linear groups correspondingly. And they will also label the reducible representations of orthogonal groups and irreducible representations of Brauer algebra. And the set of reducible representations for Brauer algebra will be a bit more complicated. So here now you can have lambda, which is a partition of n minus 2r, and r can be an arbitrary number essentially between 0 and n over 2. And the condition for the local dimension is a bit different. Now the sum of first two columns in the Young diagram lambda should be at most D. And the statement for this Brauer duality in this equivalent form is completely analogous to the Schur-Weil duality statement here. Yeah, except now here you have reducible representations of Brauer algebra and orthogonal group here. Okay, so now I introduce very briefly these elements of representation theory, and what we will need to understand the spectrum of those uses of the sum of the Euclid-Murphy elements, which I introduced a couple of slides ago, this JS and JB. And in order to do that, we need to have a concept of the content of a diagram. So given a Young diagram of size n, so mu is a partition of n, so the content of mu will be a sum of contents of all cells in mu. Okay, so what do I mean by a content of a cell? So you can draw a Young diagram. Let's say this is our Young diagram, and then you put the numbers, the integer numbers like that. So like across the main diagonal you put 0, right? Across this kind of first diagonal you put all ones, all twos, all threes, on fours, and so on. And in the opposite direction you put correspondingly -1, -2, -3, right? So and then this number in the cell will be a content of the cell, and then the content of the full Young diagram will be just a sum of contents of all those cells. Right? So in that particular example, like you can see that -3 will cancel with 3, 2 with -2, and so on, and you'll get only 4 at the end. The content of this Young diagram is 4. So hopefully it's clear. What do I mean by content of a Young diagram? And now, once introduce this content, I can just state that the spectrum of this Euclid-Murphy element JS, if you use this decomposition of your underlying Hilbert space, like here, into this direct sum of tensor products of irreps, you will see that this matrix, you need to conjugate this matrix because this matrix is written in the standard basis, right? You need to do some basis change. Then once you do it, you will see that this matrix will be block diagonal, right? And on each irrep, it will be just identity matrix on the two registers here in the Schur-Weil duality, and the eigenvalue will be just the content of the diagram. And similarly, the spectrum of this of the sum of Euclid-Murphy element for the Brauer algebra, this JB matrix, will be very similar. Except you'll have some additional term here. So you'll have like a content of lambda minus n minus size of lambda. Size of lambda is just the number of boxes divided by 2 times d minus 1. Yeah. So these are pretty standard results in representation theory of symmetric group and Brauer algebra. And we will exploit it to solve our problem later. And finally, I need a last mathematical ingredient is to explain how you restrict reducible representations from Brauer algebra to symmetric group. So let's say we have this irreducible representation of Brauer algebra W lambda, and we want to just look how this representation will decompose into irreducible representations of symmetric group, which is, or as a symmetric group algebra, right, which is a subalgebra of the Brauer algebra. So it will be decomposed into direct sum, right, of irreducible representations, but there might be some copies of the same irreducible representation, and this is encoded by those numbers m, lambda, mu. These numbers are called multiplicities, of the restriction, and we would be interested in understanding the set omega and d, which is just a set of all pairs lambda mu, such that this multiplicity is not zero, right? So basically, this set just encodes which irreducible representations mu will appear in the restriction from the representation lambda. Unfortunately, there is no easy description of the set, and there exists an algorithm which you can run it. It's not difficult to implement, but somehow the analytical understanding is missing in the literature. But luckily, for our purposes, we don't really need the full description of the set. It turns out that for our results, we would need only a certain subset of this omega, which we call gamma and d. And this is like a very specific set of pairs lambda and mu. So lambda here are just vertical Young diagrams. So here m is the size of, or is the length of the first column, right? So you have only one column here. And this R of mu is a number of rows which are of odd size in this diagram mu. So it's very strange, but yeah, but it is what it is. Yeah, as I said, if your lambda is of this kind of one column form for some number m, then actually yes, this pair lambda mu belongs to omega if and only if lambda and mu belongs to gamma, right? So basically the gamma characterizes the set omega conditioned on the fact that lambda of this form. And it will turn out that this is the only set which we will need for our proofs. Okay, so now I'm ready to present the main results. And so yes. Now let's quickly recap again the representation theory, which I already mentioned, but for this specific case where you have only two systems, n is equal to 2, and local dimension is at least 2, right? So in this case, oh, sorry, I forgot a hat here. So yeah, I wanted to say that the set of irreducible representations for symmetric group only those two Young diagrams. So this horizontal one corresponds to a symmetric irreducible representation. This corresponds to antisymmetric. And those epsilon will be projectors onto those irreps, right? So like in the standard basis. So this identity is just identity, and this F is just a swap operator or a flip operator. Similarly, yeah, again, I forgot to put a head here. These are the set of reducible representations for Brauer algebra, and now you have this additional empty irrep, and this empty irrep will correspond to a projector onto maximally entangled state. So this W is a matrix corresponding to this diagram, yeah, which you should think about as being a projector onto maximally entangled state, and yeah, you need to properly normalize it to make it to make it into a projector. And then yeah, you have a reducible representation corresponding to this horizontal Young diagram, which is like a symmetric, which is like a symmetric irrep. Oh, sorry, actually, I made a mistake in the previous line. So here should be a plus here and minus here, right? Yeah, so here, this one is the same as this epsilon, is two horizontal boxes, minus this projector onto maximally entangled state. Yeah, you basically split this symmetric irrep into two irreps when you go to Brauer algebra. And this one is the same as epsilon, two vertical boxes. Yeah, so with this notations, we can say equivalently that if you have a Werner state, it's equivalent to say that your sigma is parameterized by p. Yeah, so now it's hopefully is clear what did I mean by p, and the p will be the kind of a number in the mixture, if you wish, right, which will correspond to this state, which is a normalized projector onto antisymmetric state, antisymmetric Europe, and 1 minus p will be like a mixture, a mixture probability, right, for the normalized projector onto maximally, onto symmetric state here. So similarly for Brauer states, if you have this condition, because of the Brauer duality, you can equivalently write your state as linear combination now of 3 normalized states, which will be given by corresponding projectors pi sub empty diagram, pi sub this vertical one, and pi sub this horizontal one. And now it's important to kind of remember that this is now a 2-parameter family, right? P and Q independent parameters in principle. And finally, isotropic states can be equivalently written in that language as a mixture of these 2 normalized states. So this is a projector onto maximally entangled state, and this is like a projector onto the rest of the space, right? And now, the rule of the game will be now, if we go back to our original optimization problem, we would like to understand the following numbers, right? So we would like to, for every edge in our graph, we want to require that our density matrix here, rho E, will be equal, right, to this Werner state, and we would like to maximize those p for every, right? So like for every edges. So intuitively, this p here, so this state kind of is the most interesting one from the point of view of entanglement. So this is like a singlet state. You should think about this one as being a singlet. So you want to maximize this p to increase the entanglement in your density matrix. So this is for Werner states. Similarly, for Brauer states, it's exactly the same, except here you put the Brauer state, right? And again, but now you want to maximize this p, and this p will correspond to a maximal entangled state, right? So it's not a singlet anymore. And for isotropic state, again, it's similar story. It's like a Brauer state with more restrictions, right? It's like you restrict the Q to be of certain relation with P, and you get this type of states here. And what we would like to do, we would like to find ideally analytic expression. And luckily, so this is the main result of our work, that we were able to find exact expressions for right arbitrary size of the Kn graph, right? That's like our clique complete graph, size n, local dimension d, right? For all such 3 states, Werner, Brauer, and isotropic. It's the expressions you can see here. Some of them are not that straightforward, I would say. And before, so I wanted to briefly sketch how we actually find those in more detail. So before I do this, maybe you have some questions about the statement of our result. If there are no questions, then I'll just continue to present the proof sketches. So let's first consider the case of Werner states. I will try to explain how one may get this formula. So we have an optimization problem, which is actually a semi-definite program, right? So this one first here is a semi-definite program. What we will gonna do, we will go and write the dual semi-definite program, and we will check the Slater condition. We will check the strong duality condition, which will turn out to be it will turn out to hold. And so it will allow us to rewrite the value of this optimization, this primal optimization, as a dual optimization. And it turns out the value of this number will be equal to the following expression. So here you see that this is a minimal eigenvalue of this matrix JS, right? And module like this absolute value of E is a number of edges in our complete graph, right? So it's like n times n minus 1 over 2. Right, but this one we already know, right? Like because I explained to you how to find the spectrum of those of this matrix JS, which is a sum of Euclid's Murphy elements for symmetric group, and you can, it turned out to be equal to the content of the Young diagram. So if you want to find the minimal eigenvalue, what you need to do, you need to go and compute the content for all possible Young diagrams of size n, subject to a condition that the size of the first column is at most local dimension d. And you want to minimize the content, right? And intuitively, it's clear what you should expect to see. You should get the following: lambda is an optimal lambda for that minimization. Why is it so? It's because this content is decreasing across the columns, right? So if you want to have minimal possible content, then you need to make columns as long as possible, but you cannot make them longer than d, right? So you will stack them like that. You will get almost a rectangle, right? But there may be some k boxes left over because n might not be divisible by d, right? So, but more formally, this is a solution for the lambda which you get, and if you plug this, you will get this answer which I showed you here. So this was very easy. Now, a bit more difficult case is the Brauer case. But again, the idea and the strategy is the same. We will write the dual semi-definite program. It will turn out to be to the following thing. So here it will essentially be proportional to maximal eigenvalue of a difference between JS and JB. What you need to note is that those JS and JB commute, so they can be simultaneously diagonalized. And now, since we know the spectrum of both of them, we can analyze the spectrum. So the analysis is a bit more tricky, right? Because the analysis now will involve those studying those restrictions, right? So you would need to understand. Ideally, you would need to understand those sets omega, but as I said, it turns out that you can get away with only knowing the simple set gamma, and so I will not present the details for that technical discussions. You can find them in the paper, but in the end, you can find this maximal eigenvalue, and it will turn out to be equal to that number over here. Okay, and so finally, the most difficult case is a isotropic case. So in isotropic case, so first thing will be to change a variable. So instead of considering this p variable, it's better to go to p prime variable. And p prime variable, again, the strategy is the same. You write the dual as dp. Turned out to be equal to that optimization. Now it's a minimum of maximum eigenvalues of such an operators here, right? So here you see that so for every edge in your graph, you have some like identity operator, a flip operator, or this W operator, which is this unnormalized projector, right, onto this maximally entangled state. And yeah, and you want to minimize it over all choices of x, which are real numbers here. Well, yeah, it's a bit more complicated. You can rewrite this thing in the following way. So it will be like a min-max problem. And here, this f sub lambda mu of x will be an affine function. So yeah, there is no need to look into detail into this expression. So there's like this free term here, and this is like a slope coefficient, right, for in front of x. But the point is that you won't like to understand this function f of x, which will be a max of those affine functions over the set omega, right? So this f is parameterized by pairs of lambda and mu, and lambda and mu come from this set omega. Well, and this is, I would say, the most difficult part of our paper, because understanding this is a bit not that straightforward. So you need to be very careful with the analysis. And so just to give you an intuition how it works. So if you introduce the following notation, like g of lambda and a of mu, right? So g of lambda is just the value of those affine function at a certain point, which is this, on this graph, it's this x tilde here. This is this point here. And a mu, just some, it's like a value of a function f at the point 0. Then, all those affine functions are uniquely characterized by pairs of points. So you can put those pairs of points, like in this, like in this graph, and through some pairs of points there will be a line, right? And this line will correspond to this affine function, and it will only be present if this lambda mu belongs to omega, right? So some pairs, and for some pairs, then they're not elements of the set omega, and you don't see them, right? So for example, this point over here and this point over here, they're not, there's no line going through them, right? So it means that this pair of lambda 1 and mu 1 does not belong to omega. And as you can see, this bold red function is our f function, right? That's this maximum of our affine functions. And what we would like to understand, we'd like to understand the minimum. And sometimes this minimum actually coincides with this black dot, but sometimes it's not. Sometimes it's a bit to the right, and you need to treat it carefully to make sure that you are correct. But again, the high-level idea would be to actually to use the part of our set omega, which we know, so this gamma set, and then what you would like to prove, you would like to prove that actually, if you would like to understand this minimum, it's sufficient to restrict to the gamma set. Basically, the pairs of points which produce you those intersections will come from the gamma set somehow. So this is the realization, and in some sense we are very lucky that we get away just by knowing gamma set and not the full omega set, which is complicated. Okay, so this is like the high level idea how you solve the isotropic case. Okay, so now I wanted to have a quick discussion of our results. So first of all, if you look at those formulas for all three cases, you can compare it with non-separability criterion for those states. So these states are well studied in the literature, and the separability criterion are known for them. So for example, for Werner states, it turns out that the state is separable if and only if this P is at most 1/2. For Brauer states, the condition is like that, and for the isotropic state, it's like this. And what you can see here, for example, is that for large enough n, this Werner state Kn extendability will always lead to separable states. Similarly, for isotropic states, you can see that if you take n large enough, it's a bit more difficult to see, but you can check it, that again, for large enough Kn extendable isotropic states, those states become separable. But this is not true for Brauer states. So if you check this condition, then for any n, no matter how large it is, like this value will be like a bit bigger than this one, right? So it actually means that this Brauer states, which give you this maximum kind of maximal entanglement possible and on the complete graph, they're actually entangled, right? They're not separable, which is an interesting feature, right? Because it doesn't hold for Werner and isotropic states, as I just explained. Another quick discussion, which I mentioned at the beginning, that I wanted to consider the case of complete bipartite graph extendability, so K and M extendability. And so I just wanted to briefly comment on that case because it was covered by a recent paper by Jakob Solimos-Simbaras. And they found that for the case of isotropic and Brauer states, the value has a very simple form like that. But for Werner states, unfortunately, this number doesn't have a nice expression. So they characterize it in, using some representation theory of symmetric group and things like Littlewood-Richardson coefficients. But unfortunately, it doesn't have a nice expression. And I wanted to mention that the case when you have a star graph, namely when m is equal to 1, this case was studied extensively before in the work, for example, in the work of Jonsson Viola from 2013. And for Werner states on the star graph, you can find the following nice formula. Essentially, the number is n plus d minus 1 divided by 2n. So very simple expression. So that, and essentially this summarizes what we essentially know about extendability, right? So now, so our work covered the case of the complete graph Kn, and the previous work somehow covered the cases of K and M extendability. And now it will be interesting for the future to maybe consider other edge-transitive graphs to solve the similar problem, or maybe even go beyond edge-transitive graphs. Maybe it can be possible to tackle expander graphs, right? Because the expanders are similar in the expansion properties to complete graphs. So maybe we should expect similar results to appear there. I don't know. Another avenue, as I mentioned, it would be nice to find a closed form expression for the case of complete bipartite extendability of Werner states. And one other question might ask, so I used classic representation theory of general linear groups, right? Like unitary group, an orthogonal group. What about symplectic group, right? And another classic group. I am not aware about results which might be somehow put in this framework of the Schur-Weil duality for symplectic group in quantum information. So I would like to learn more about this, and if you have some ideas, I would like to chat about this. And as I said, the concept of monogamy is very fundamental in quantum information, and we still surprisingly know not a lot about it, right? So, and in the context of extendability, there are a lot of work to do. So, with that, I would like to thank for your attention.
All right. Thank you very much for a nice presentation. We're going to open to some questions right now, if the audience has them. So do we have any questions?
Sorry, I'm not familiar with this Brauer duality. So is there any intuitive way to understand the Brauer duality, why it is useful for this monogamy problem? I mean, it's easier to understand Schur-Weil duality because they are discussing symmetric group and yeah, the unitary group, something like that. But what was the understanding of Brauer duality? Can you give some intuitive understanding? I'm not familiar with this.
Yes, so I guess maybe the most intuitive way, I would say, so you might, but I bet you might know about this kind of a transpose trick, so like if you have a maximally entangled state, right, a bipartite maximally entangled state, and imagine you act on this with the matrix like A tensor identity, right? So this thing will be equal identity tensor A transpose, right? And now you see that if your matrix A comes from orthogonal group, right? So the action of complex orthogonal group, basically the state will be invariant under the action of complex orthogonal group. And yes, so this is the intuitive reason why those diagrams now have horizontal pairings, because these horizontal pairings, they will correspond to the to maximally entangled state projector, right? And if you act on this maximally entangled state projector with the matrix of the form O tensor O, where O is element of orthogonal group, it gives you the same thing back. Yeah, so this is why in that case you get an algebra which is bigger than just a symmetric group algebra. Now you have these horizontal things. Yeah, and this is how you should, I guess, and imagine how it works. Yeah.
Okay, I see. So at the end of your second part, you mentioned the gamma state, and this gamma state is important. Can you explain it more?
Yes. So let me just. Okay, let me just maybe go to. Yeah, let me just go to. So do you see the slide, right? So the slide 15, right, at the moment.
Yes.
Yes. So. So in this case of Brauer's thing, right? So what you see here, that you want to understand the maximal eigenvalue of the difference of those JS and JB matrices, right? And so JS, it's so we know the spectrum of this one with respect to like Schur-Weil duality for for symmetric group, right? And for JB, we know the spectrum for Schur-Weil duality with respect to Brauer algebra. And so the point is that if you if you look at the and the maybe I'll go into here. Yes, so here, so you see this JB will have certain eigenvalues and JS will have certain eigenvalues, but it can happen, right, that this lambda, so right, because the symmetric group algebra is a subalgebra of Brauer algebra, it means that this identity will be decomposed into direct sum of different identities of symmetric group, right? Because that is what happens when you restrict irreducible representations. And that means that, and then if you consider the, the difference of those elements, you will be subtracting this number from that number. So that number will be a function of mu and lambda. And so which pairs of mu and lambda will appear? So the answer is that only the pairs for which the multiplicity is non-trivial, right? Because if the multiplicity is trivial, it means that this irreducible representation doesn't appear in the restriction. And that's why it's important to know which irreducible representations of symmetric group mu here appear, right? So you need to know this at omega to just understand what are the all eigenvalues of your matrices JS minus JB. Yeah, so that's why understanding this omega is important. But then somehow very, it's a miracle in a way that it turns out that you in the end to obtain our results, you don't need to understand the full set. It's complicated. It has complicated algorithmic description. There is no kind of easy like human understanding of it, at least to my knowledge. And but yes, this set gamma is very easy to understand. And yeah, it's really a miracle in a way that only knowing this gamma is sufficient for proving the results in the end. That, yeah, so this is why understanding this is important. Yeah.
Okay, thank you. So final question. Your technique looks very interesting, but so this can be applied to any graph, or is there any constraint for applying this?
The question is, can it be applied for any graph, right?
Yes.
Right. Yes. I think no. I think this is very specific for this very symmetric graphs, right? Because in the end, I reduce my problem to this Euclid-Murphy, like the sum of the Euclid-Murphy elements, right? And the sum of Euclid-Murphy elements are very specific elements, right? And yeah, I managed to use it only because my graphs were like, yeah, essentially was a complete graph in my case. I think you can still use it for example, for bipartite, a complete bipartite graph. So and you will obtain a different type of proofs which are present now in the literature from other papers which I mentioned. But for other graphs, yeah, I thought a bit about it. I couldn't really find a nice example where I can use it, fortunately. Yeah.
I see. Oh, okay. Thank you for the very nice talk and work. Thank you.
Yeah. Thank you very much for your questions.
Okay. Do we have more questions? While the audience think, oh, I think we have
yeah.
So Jello.
I'll maybe just ask something. Is that okay?
Yeah.
Yeah. So I think from the way that you parameterize the states with in terms of P, so I believe Werner and isotropic states should match, like for dimension 2, because they will be locally unitarily equivalent.
Yeah.
I think
For
the
dimension 2,
yes. For the way you parameterize it, so I would expect you get the exact same result in the qubit case.
Yes. I think you're. Yeah, I think you're right. I mean, I should get the same.
I mean, of course,
actually,
I suppose I could just see it in the paper. I just wanted to ask you directly.
Yeah, actually, I didn't really check it for myself, but yeah, I can quickly see, right? So maybe here, yeah, if I plug d equal to, let's say, for Werner, and here, yeah, it's a bit difficult to see from this formula.
Yeah, but, it's not so obvious. Yeah, okay, but anyway, yeah, I know. Okay,
but yeah,
I suspect that that's the case. Yeah. Okay. Yeah. That's for. No, that's all I wanted to ask for now. Yeah.
Yeah. Thank you.
Okay, I do have a very short question associated with this. When you compare with the canonical results that we have for the states in regards to their separability and the parameter P, I noticed that on the Brauer case, it also depends on Q, but I think your result doesn't mention Q. So why is this the case?
Yes, it's a good question. So it's a technical detail which I put under the rug for my presentation. Yeah, but you know, it's explained in the paper. So let me just explain it here. Right. So my optimization problem here for Brauer state, as you can see, it's like 2-parameter family here, P and Q, right? Optimization variables, but I really want to maximize P only. It's like you need to prove a separate claim that when you attain the maximal possible P, Q is actually equal to 0. You can prove this. So actually, so basically, like the true statement is that when you obtain this maximal value, so this is the maximal value, right, of P possible. For that maximal value, Q is actually equal to 0. And yeah, you should kind of remember this. So it's because, yeah, so you should imagine that you have a plane, right? You have PQ plane, And in this PQ plane, you have like a polytope. And what we are doing with this optimization, we're kind of finding only one extremal point of the polytope, right, where the P is maximal. But actually, there is like a whole polytope out there, so which would be actually interesting to understand. And actually, yeah, I didn't really mention that as an open problem, but yeah, it will be a nice open problem to characterize this PQ polytope for Brauer states, like in full. So because right now what we are doing here, we are just characterizing only one extremal point for which P is maximal.
Okay. Okay,
Yeah.
I understand. All right,
Yeah.
thank you.
Yeah, thank you for your question. Yeah.
Let's just wait.
Can I ask another question? No,
yes.
Yeah. So, okay, so when you do this like extendability, right? So, does it tell me anything about whether the extension is unique?
Yeah. So, well, okay. So here I'm really kind of.
Of course, like I'm sort of thinking in terms of like some marginal problem, right? Where you're requiring the reduced states to be the same state. But I guess even in the marginal problem, it doesn't care whether the solution is unique or not. It only cares whether it exists.
Yes, here I don't really care about uniqueness, right? It's like in a way I'm caring about feasibility only, in a way, right? And yeah, like you know, like because I think those solutions will be highly degenerate, and like meaning that you can choose even some mixed states. You know, you can choose pure states, and then you can maybe take some kind of mixture of different pure states which lie in the eigen, like in some eigenspace, which have this, right? Like you can take some pure states from the same eigenspace of, or you know, of your Hamiltonian from this dual SDP, I would guess, and then maybe you can take a mixture of those pure states, right? So you'll get another solution. Yeah. So yeah. So my guess that actually solutions are really very non-unique in a way.
Yeah, I was just like wondering whether, because it's also very highly symmetric, and normally this also constrains what possible global states you would have. Yeah, but of course, I guess you don't really get the uniqueness information for free. It's not clear.
Yeah.
Okay. Again, thank you.
Yeah, it's like you. Yeah.
Okay. Also, before we